All right. So tonight we're going to look at volume. We're going to look at two different methods to find volume. We're going to look at the cylinder method and then the disk method. So when we're looking for volume, we're looking for at a three-dimensional shape. So we're taking our functions and we're going to be rotating them around an axis. And it doesn't necessarily have to be the x or the y-axis. It can be any other value too. We can do it around the x minus 1 or x plus 1 or y equals 2, anywhere we want. We can shift it up and down to rotate it. It won't change the actual values, but it will change the radius and where we're calculating the actual functions from. So we're going to look at a couple examples of that. So typically you can find volumes of cylinders and rectangular boxes. Those are pretty simple and straightforward. You'll probably learn those in middle school and if not in high school geometry. So we've got those formulas. The problem is when we start looking at shapes that are a little bit crazier, like this shape. It's like it's not a uniform shape that we're going to be able to find the area of it or the volume of it. So when we're looking at finding the volume of a shape like this, we need to look at the functions that actually make the curve of that shape. And then we use that to do the actual calculations of it. So one of the methods when we're looking at doing like a Riemann sum, we break it down into pieces. Same thing we were doing with the area. We break it down into smaller and smaller pieces. And we're going to basically add those together, which is what integration does. So if you look at this, that's my Riemann sum. It's the limit as n goes to infinity of the area of that disk that I'm looking at. So it's basically just the integral from a to b of the area of that disk. So we're looking for that area when we're looking at our functions. So we're looking at the cross section of it. So that the area isn't going to be a fixed area because we're not looking at just one specific disk. We're looking at that disk as it changes from the beginning to the end. So it's always going to end up being a function at that point. Also, when we're looking at, depending on the functions that we're going to have, we could have multiple functions that we're going to have to do the subtraction for, just like we were doing with the areas on the last class. So let's look at a simple example. We're going to figure out, we're going to basically prove that the volume of a sphere is 4/3 pi r squared. The reason we start here is because we know the function of a circle, so it makes it a little bit easier to find out the area, the cross-sectional area. So if we place the disk, so we have a disk, and we're just going to move from the edge all the way across. We need to figure out that radius for it. So the radius of my circle, if we know the specific point on it, is we use the Pythagorean theorem. So y equals the square root of r squared minus x squared. That's going to give me that radius of the disk because I don't really want the radius of the sphere. I want the radius of the disk that I'm looking at. So that's why we're looking at that y value right there. And I just realized you can't see my actual mouse pointer. So I'm talking about things and you can't see the pointer. Laser pointer. Laser pointer. There we go. So we're looking at that y value right there. That's the radius that I'm looking at, not the radius for the actual sphere. So the y equals the square root of r squared minus x squared. So that circle right there is pi times the radius squared. So the area is pi y squared, and then y squared is basically just r squared minus x squared because it cancels out the square root. That part makes sense? Because now we're just going to do the integration of it.
Yeah, that makes sense.
All right, let's do the integration. Okay, so when we're looking at this one, if we go, actually, we'll go back 1 second. We're looking at it from the negative r value all the way over to this r value. We're going all the way across the sphere. So when we have our integral, we're going from negative r to r. Now, if we're thinking about a sphere is obviously symmetrical. So we don't necessarily have to go from negative r to r. We can go from 0 to r and just multiply it by 2. So the area is pi times radius squared minus x squared. Remember, in integration, we can pull out any constants. So I can pull out that pi. So that's why there's a 2 pi in front now. And we're looking at the integral from 0 to r of r squared minus x squared. So the integral of r squared is r squared x, because we're integrating by x, not the r. So the r is not changing. The r is basically, for all intents and purposes, a constant in this situation. And then we have x squared, it goes to x to the third over 3. We're plugging in the 0 and the r. So when we plug in the r to the r squared minus x, or r squared times x, we get r to the third. And we plug in the r here, we get r to the third over 3. The 0 is going to cancel both of those out, so I don't need to worry about the 0 term. R squared minus r to the third, or r to the third minus r to the third over 3 is 2/3 r to the third. And if we bring that out, that's how we get the 4/3 pi r cubed. So this is basically proving that volume using integration. But it's also showing you how we use the disk method to find the volume of a specific shape. So if we look here, we've got, that's basically what it's doing, is it's using the disks to cut it down further and further. So, and as you can see, the more disks we use, the closer it's going to get to that 4/3 value. Or 4/3 times pi. So our area, since we're looking at our disks are going to be circles, our area is always going to be pi times the radius squared when we're plugging it in. So when we're looking at my formula, the integral, it's going to be, that area is going to be pi r squared basically. The r is what we're actually going to be looking at in terms of the y's and things like that to figure out the values at our functions. And we can do it on the x-axis or the y-axis, depending on which way is going to be easier for us to figure it out. All right, let's look at one example of this first before we go on to the next one. That one. All right. Can everybody see this?
Yes.
All right. I'm going to write the function out a little bit bigger. So if you can't see the function, it's okay. All right, so we're looking at the y equals the square root of x as my function. And we're going to rotate it around the x-axis. So when we're doing this, the first thing we have to come up with is what my area is. So if we look here, actually I'm going to make that a little bit bigger because it's small even on my screen. That's better. Now you can see it a little better. So we're looking for, that's going to be my radius right there, going up and down. So in this case, my radius is the square root of x.
How did you decide that?
Because so we're looking for we're rotating around the x-axis. So we're rotating around there. So the radius is going to be from the x-axis to the edge of the curve. And in this function, my curve is y equals the square root of x. So at 1, it'd be the square root of 1 would be my radius. At 0, it's going to be the square root of 0. And everywhere in the middle, it's just going to be the square root of whatever my x value was, would give me that y value. Make sense or no?
Yeah, at first I wasn't sure where that came from, but I get it now.
Okay. So remember our formula, we're looking for area is pi r squared. My r in this case is going to be the square root of x. So my area is pi x. Because it's r squared, So, or the square, I can square this real quick, which is just pi x. So my integration, the integral, in this case, we're going to do it from 0 to 1, because that's what we're looking for on that curve, from 0 to 1. And my area is pi x dx. So the pi can come out, and I'm just looking for the integral of x. So it's pi x squared over 2, evaluated from 0 to 1. So it's 1/2 pi. And when I plug in the 0, it's 0. So the answer is 1/2 pi, or pi over 2, depending on how you want to write it. Honestly, the absolute hardest part of this is not the integration, it's finding the radius. Once you can find the radius, the rest of the stuff's actually pretty easy on this stuff.
Will there be problems where they won't give us the radius, like they'll expect us to do that?
Most of the problems are either probably not going to give you the picture of it. You're going to have to do the graph and figure it out. But they're always going to give you that function, which is allowing you to figure that part out.
Okay.
I just stole the pictures from the book because I didn't feel like trying to draw them while you guys were sitting there staring at me, because I'm not a really great drawer. So, but you can use Desmos to actually just graph it and look at the curve, and then once you figure out where you're looking, it's pretty simple to go through and do. Some of the more complicated ones you could find the pictures for.
On an exam, we can use Desmos and the book, or no books during the exam?
You can use Desmos, you can't use the book.
Okay. No open notes either? Nothing?
So typically what I recommend is, actually even when I have class, what I'll do is I'll tell you guys, you can use an index card. So I'd have you write down all your formulas and stuff on an index card to use. The reason I have you guys do that instead of just open notes and open book is it kind of forces you to go through and actually study and write down what you need. When people have open notes and open book, they spend half the time looking through their book to find the actual answer or in their notes, and they waste a ton of time on the test. By going through and making the index card, you write down the formulas and everything that you need as you're studying, and it basically simplifies the test a lot more and helps you study. So I would suggest doing that too.
Yeah, sounds good.
All right, let's look at the next one. So we're going to go to example 4. So this was a little different. It's a little more complicated. Actually, yeah, I got to go back to my PowerPoint real quick. I'll just do it this way. All right, so the next thing we're going to look at is, if you notice on this shape next, let me make it a little bigger. I have a big screen and a little screen that I'm looking at, and I notice on my little screen it's really small. So if you notice on this one, when we take that shape, so we're looking at the region enclosed by y equals x and the y equals x squared. So it's not going all the way down to the x-axis, but I'm still going to rotate it around the x-axis. So now instead of being a solid disk, I actually have a donut. So when we're looking at the area of that donut, we have to subtract out the center or the whole of the donut. So when I'm doing my area, my formula for area is still going to be pi r squared, but it's going to be pi, and it's the outer squared minus pi inner squared. So we're subtracting off the inner radius from the outer radius when we're actually going through and doing it. So just keep that in mind when we're looking at these type of things. We're still looking for that radius. We're still looking at for that little line, but we're always going back down to the actual x-axis or wherever we're rotating it around. So in this case, we are going to the x-axis. So we're looking for that little line right in the middle there. So in this case, my area, the outer is x, and the inner is x squared. Now, depending on where we're going from into, so in this case, we're looking at it from 0 to 1, because that's where those two lines cross. The x squared is actually less than the x. That's why it's that second one. So that's where, when you're graphing it, to be able to figure out which one's on top, which one's on the bottom, the same thing we were doing with the area in section 5.1 is very important, because at some points they switch over and you'd have to have x squared on top of the x. So we're going to do the exact same thing. We're just going to set up my formula. So I'm going to do one thing to make my formula a little bit simpler. I can factor out the pi. So I have x squared minus x to the 4th. So we're going to do the integral from 0 to 1 of pi x squared minus x to the 4th dx. The pi can come out, so I'm not really worried about that. So it's pi, and we're doing, so it's x to the 3rd over 3 minus x to the 5th over 5, evaluated from 0 to 1. So now we're going to plug in the values. So the 0 cancels everything out, so I don't have to worry about that one again, which is nice. So I've got 1/3 minus 1/5. So the answer ends up being 2 pi over 15 is the area of, or the volume of that cone that's made. Any questions on that one? All right. So I'll do one more disc one or donut one, and then we're going to go on to the cylinder ones. So the only difference on this one is where we're rotating it around. So on this one, it's actually the actually we didn't. So we're actually going to use the exact same curves. We're still doing the y equals x and y equals x squared. The difference in this case is where we're rotating it around. So we're going to rotate this one. Instead of going around the x-axis, we're doing it around y equals 2. So it's shifting up here. That's going to be my rotation point. So when I'm looking for my radius and I'm looking for which values outside and which radius is outside and which radius is inside, that's what I have to keep in mind. I'm doing the radius to the rotation line. So in this case, the outer edge is my x squared. So it's going to be 2 minus x squared is going to be the y. And then my inner one is going to be 2 minus x. Because I'm going from, I want to figure out how far it is from that line to the x value. Does that make sense?
So if you were doing it y equals -2, would it be 2 plus x squared? Like, I guess I just don't know why do we need the negative sign, the minus sign?
So yeah, let me actually show you. So here's my x squared line. All right, so if we're looking at it, if we're rotating it up here, this is at 2. So that's y equals 2. I'll do the -2 one too, so you can see that one too. So if I'm going from here to here, let's say that right there, that's at x equals 1. So that radius right there is really only 1. That's 2 minus 1 is how long that line is. Let's say if I'm at 2, actually I can't do 2 because 2 would actually work. If I did 1/2, that would end up being 2 minus 1/2 to get down to that point. So that line would actually be 3/2 long. from that line of 2 down to the value of that function. In the example that you said, well, what happens if we did it around -2? So now if I'm going from here up to that line, would actually be the x squared plus 2, because I'm going to add this value right there to whatever value was the y value that was going up to the function. Okay. So you're always looking at how long that line is from the center line to the function that you're doing. And that's why in this case, it's the 2 minus. Nope. Everybody got that part? Like I said, the hardest part is finding the radiuses. I'm actually probably going to do one more after this one with radiuses so you can see the other one. All right, so let's go through and do this function out. I'm going to erase this. See if we actually get the answer for it. So when we're going through and doing this one now, my area, the outer edge is 2 minus x squared squared, and then the inner one is 2 minus x squared. So that's the other reason we have to really think about what's the inside, what's the outside. And the last one, the x was first and the x squared was second, because we're rotating it around. And this one, it's reversed to that. So we're going to do our integral. We're still doing it from 0 to 1. And I'll pull the pi out so I don't have to worry about the pi. So it's 2 minus x squared squared minus 2 minus x squared. So go through and do our foiling, everything else, and we end up getting x to the 4th minus 5x squared plus 4x. The 2's cancel each other out. That's where the 2's ended up going. I will tell you the biggest mistake that people make on all the tests, and I'm pretty sure this probably happened in Calculus 1 too, is algebra. Most of the errors that I've seen and see is with foiling and with signs. So do be very careful when you're going through and doing your foiling out. My biggest pet peeve in the world is seeing people foil 2 minus x squared and getting 4 minus x to the 4th and completely forgetting about the middle term. So just keep that in mind when you're doing out your foiling to foil correctly. All right, so we're going to do our integration for this, and we get pi x to the 5th over 5 minus 5x to the 3rd over 3 plus 4x to the squared over 2, which yes would reduce to just 2. Now we're doing it from 0 to 1. So I've got 1/5 minus 5/3 plus 2. The zeros cancel everything out. So my final answer is 8 pi over 15. Is going to be the area or the volume of that shape that we have, because it actually doesn't come to a point, so it's not even actually a cone at this point. Add one there. All right, we're going to do the exact same shape, actually. We're going to do the exact same functions. But this time, we're rotating around x minus 1, or x equals negative 1. So same functions. I have y equals x and y equals x squared. But this time I want to rotate it around x equals negative 1. So since we're rotating around a vertical axis this time, I want everything in terms of y. This is going to make our lives a little bit easier when we're doing our calculations. So the first one, I don't really have to change because it's just x. Second one, I'm going to change to x equals the square root of y. I don't have to worry about the plus or minus version of it because we're looking at the radius on one side, and we're going to rotate it around. So I don't need to worry about the negative version of the square root of x or the square root of y. The next thing we have to look at is, what is my radius? So if we look at the radius from this point over, so we have, that's going to be 1 over to the y-axis. And then I have to add the distance to the actual curve. So my inner curve on this one is the y. So my inner is 1 plus y. And my outer is going to be 1 plus the square root of y. Everybody see how we got that?
Yes.
Then we're getting better at finding radiuses, which is a very good thing. All right, so now everything else is the same. So my area is going to be pi, and I have 1 plus the square root of y. That was a horrible 1 plus the square root of y squared minus pi 1 plus y squared. So my integral, we're still going from 0 to 1. And actually, I'll pull out the pi before I do this. So I have 1 plus the square root of y squared minus 1 plus y squared. And we're doing dy. All right. I'm going to FOIL this one out just so you can see it. Because of the square root is in there, it makes it a little more complicated when you're dealing with the exponents. And I want to make sure you actually see what the values are. So we have 1 plus 2y to the 1/2 plus y minus 1 plus 2y plus y squared. So we get pi 0 to 1. The ones are going to cancel out because I have 1 minus 1. I have 2y to the 1/2. Then I have minus y and minus y squared.
That 0 to 1, you just took it from the previous problem, right?
Yeah, we're still working on it from that 0 to 1 because that's where they actually intersect.
Okay.
So that's why we're still using the 0 to 1. You actually can use any, the reason why we could use anything less than 1, but if we went beyond 1, we would actually have 2 different integrals we'd have to do. We'd have to do the integral from 0 to 1, and then we'd have to do the integral from 1 to wherever, because they switch at that point. So we'd have to do it like we did the sine and cosine one last week.
And then you just add the 2 different sections, right?
Exactly, yep. So now we're going to do the integration of this one. So we do our integral, and we get 4 y to the 2 or 3 halves over 3 minus y squared over 2 minus y to the third over 3 from 0 to 1. So we have pi 4/3 minus 1/2 minus 1/3. So we end up getting pi over 2 is my final answer.
So say the points of intersection were 0 and then 1. Since you're going off the y-axis, it would need to go from 0 in that instance, right?
Hold on, repeat what you said because you cut out like twice right at the most important part.
So right now the points of intersection are 0, 0, and 1.
Yep.
So if it was 0 and 1, 2, in this instance, you would have to go from 0 to 2, right?
Yes.
Okay.
Yeah. Because you're looking at the y values, not the x values. All right. Switch back over to the PowerPoint because we're going to do the cylinder method now. All right. So that is the disk method or the donut method when you're looking at ones with holes. So there's two different methods that we can use to do this. That was the first method. The second method is by cylindrical shells. So we're actually looking at a cylinder that goes around instead of just a circle. So they have certain problems. It works better. The nice thing is every single problem you do, you can do either way. So you can just say, okay, I'm always going to do it by the disk method, or I'm always going to do it by the cylinder method. It is completely acceptable to do that. Just realize some problems are going to be harder to actually find the integrations for because the functions will be a little more complicated in that way. The reason why we have them both is because we can take something, if we're rotating it around the x-axis, and use the y values, solve it for y instead of having it solved for x. And vice versa. If we're rotating around the y-axis, we can have it solved for x instead of solving it for y. So that's really what the two methods do. So it depends on which function is going to actually be easier to solve. And we're going to look at one that we already did so you can actually see the comparison between the two. So if we're looking at this function here, so we've got the y equals 2x squared minus x to the third, and we're rotating this around the y-axis. So if we slice it the way we've been doing, you'd get a washer. So the problem is to solve that, we need to solve this for x. Now, if you try to solve y equals 2x squared minus x to the third for x, you're going to be there for a while. Actually, I don't know if it's completely and utterly possible to do. So we can't really solve it for y to do the integration by y. So we want to leave this equation as is to be able to solve it out. So we're going to look at doing it as a cylinder method. So if we rotate it that way and we're looking up and down, so we're looking at it in terms of the y, it would actually make a cylinder going around it. And if we find the volume of that cylinder, we can then do our calculations. The nice thing is that the only difference between looking at it as a washer or a cylinder is we're going to take it and multiply it by its height. So the radius is still going to be there. We're just using the extra height value. So the volume of a cylinder is the V2, or subtracting the outer and the inner, because we're always going to have an outer and an inner value for our cylinders. So our cylinder is pi r squared times the height, and then the second one. So you end up getting the 2 pi r squared plus 1 r1 over 2 times the height, and then subtracting those two. This looks really complicated. It's going to get simpler in a second. So we're letting instead of looking at the radius as it's changing, we're just going to look at it as the change in r. because that's going to be the difference between those two, the two values. So the change in R, so it's now the volume equals 2 pi, the change in R, or times the height value. So we can remember it as the circumference times the height times the thickness, because 2 pi R is circumference. So we have our circumference times the height times the thickness, how thick that shape is. And that's going to go down to 0 because that's the entire point of integration. So that value you don't really end up using. You're just going to use the circumference times the height. So you can see here, we're cutting it down. We use it as, those are the cylinders that I'm going to get. And each cylinder gets, as it gets smaller and smaller, you get a more accurate representation of the curve. So we have our integration right here. It's the integral from a to b of 2 pi x times the function of x, which is the height, times dx. So that's the equation that we're going to use for this. So the integral, unlike the last one where it was just the area, this one is 2 pi times x times the function of x. And if we're doing it across the y, or for y, it'd be 2 pi times y times the function of y. And we will do one of each. So there's that function again. And you see, that's my circumference part, that's my height, and then the dx is the thickness part. Any questions on how we got that formula? All right. So let's go back to the example that we were looking at, the y equals 2x squared minus x to the third. So we're taking this shape and we're rotating it around the y-axis. So as we look at it, my radius, that's my circumference of this, is 2 pi x. And my height is the 2x squared minus x to the third. So I've got my circumference, I've got my height, and I've got my thickness. So we can pull out the 2 pi, because that's just a constant. And then I'm going to multiply the other things by x, so I get 2x to the third minus x to the fourth. And then we're going to do the integral of that one. So I get 1/2, or x to the fourth over 2, and x to the fifth over 5. Plug in the 0 and the 2, because this one's going from, we're going from there all the way over to 2, because that's where it crosses back over the x-axis. We get 8/32 over 5. So my final volume of this shape is 16 pi over 5. So on this one, it's, the nice thing about this one is the radius doesn't matter as much. It's the height that's actually going to matter in this case. Is the piece we really need to look at. Yes.
2x squared minus x to the third is the height, but isn't it also the radius technically?
It would be the radius if we were doing the disk method, yes. So, but in this situation, we're looking at it, it's from the x-axis up. So we're not rotating around the x-axis. If you're rotating around the x-axis, that would be the radius. But since we're rotating around the y-axis, that ends up being the height of my cylinder. As I said, in essence, it basically is, instead of looking at the radius in this case, we're looking at height in this case. All right. That one. So we're going to go back. Let me switch over to my other thing now. That. All right. We have this shape. We've already done this shape. So actually, let me go back real quick. So one of the first problems we did was we looked at the curve y equals the square root of x, and we were rotating it around the x-axis. And we had to find our radius, and we did our formula based out on that one. So this one we were doing with the disk method. We're going to do the exact same function now, but this time we're going to use the shell method. So we need to have the equation. It's the opposite way when you're looking at the disk method. So when we're looking at the cylinder, if we're rotating around the x-axis, I want my equation solved in terms of y. So solve for x. If I'm rotating around the y-axis, I want them solved in terms of x, so solve for y. So since my original equation was y equals the square root of x, if I solve that, it's x is going to equal y squared. That's going to question. Yes, radius and height just depend on which method we're using. So now I'm looking at my height from here to here. That's the height of my shell. So since it's 1 minus y, it's y squared is going to that function, and it's all the way over to y, 1, since this is the actual endpoint, and that's what I'm looking at going to, my height is 1 minus y squared. Because we're actually going to find out the height going back to this value here. So it's 1 minus that. The value is going to give me the height of my shell, because that's what's inside of the curve. So my height is 1 minus y squared. So my function is going to be 0 to 1, and it's 2 pi y times 1 minus y squared dy. So the 2 pi can come out, and I have y minus y to the third, which gives me 2 pi y squared over 2 minus y to the fourth over 4 from 0 to 1. So it's 2 pi 1/2 minus 1/4, which is still pi over 2. So it's just two different methods to find the exact same answer. So, and honestly, in this problem, the disk method was easier because I didn't have to deal with the 1 minus or anything else like that. It was just the square root of x. But I did want to show you that you actually can find the answer the same way with both functions, because I think that actually is a very important thing to recognize. Questions with that? All right. Okay. Go to one more problem. All right, so let's look at this one. So I've got my two functions. So I've got, or my equation is y equals x minus x squared. And y equals 0. The homework's actually right in the book. I'll show you in a minute after I'm done with this problem. And we're rotating this around x equals 2. So this is going to be my rotation point, right in the middle there. So my function, I have an inner, so since I'm rotating around 2, this function stops right there. So it goes down. So I do have an inner and an outer part to this one. So, well, actually I don't. I have the radius is going to be a little different than just x in this case because my radius is not going all the way over to the axis. So my radius of this is actually 2 minus x because I'm subtracting this part from it. So figure out how far it is from there to there. Okay. So when we're rotating it, sometimes if we're especially when we're shifting it off the axis, that's when your radius is going to change. That's where you have to look at that part too. The height probably is not going to change as much, but when you're shifting it, that's going to change. If you were shifting it up and down, then your height will actually change a little bit. So in this case, my radius is 2 minus x, and my height is my function, the x minus x squared. So I'm going to do my equation. My function is going to be from 0 to 1, because that's where it starts and where it hits the x-axis, or the y equals 0. So then I have my 2 pi times my radius, which is 2 minus x, times my height, which is x minus x squared, dx. So we can pull out our 2 pi. Then we're going to FOIL this out, and we get x to the third minus 3x squared plus 2x dx. So 2 pi x to the fourth over 4, 3x to the third over 3, and 2x squared over 2 from 0 to 1. So 1/4 minus 1 plus 1, which is just 1/4. So it's pi over 2. Ends up being my volume. They like pi over 2. So the last thing we're going to look at here. So really the two things you have to figure out is the radius is the big piece when you're looking for the discs. The height and a little bit of the radius is what you're looking at when you're dealing with the cylinders. The key to figuring out which one you want to use is where you're rotating and which function is going to be the easiest way to do it. So if we're rotating around the x-axis, you're going to use it's going to be y equals for your functions. It's going to be f of x. If you're rotating around the y-axis for the discs, it's going to be f of y. The cylinders is the exact opposite. If we're rotating around the x, we're going to use f of y. If we're rotating around the y, we're going to use f of x. So it's really a matter of which function is easier for you to deal with when you're trying to solve it. And that's where you'd actually make that decision. But each one of them you can technically do. So every one of them, if you could solve it for f of x or f of y for the discs, you can use those. you can solve it for f of x or f of y, you can use the cylinder one for it. Most problems, it's going to be easy enough to transfer back and forth between the two. It's just a matter of, can you do the integration easily enough? So depending on how complicated the function becomes when you solve it, makes the integration a little bit harder. That's really the only actual difference between the two. All right. I'm going to stop the recording because that's technically it.